Hello everyone, we are Yunji, Choi, and Jiyoon Kim. Today we'll explain the concept of nitrogen vacancy center in diamond, which is one of the most prominent quantum materials. We'll focus on explaining the science behind it in detail. So to start off with, a simple question arises. What exactly is nitrogen vacancy center in diamond? Nitrogen vacancy center in diamond is a specific type of point defect in the diamond lattice. It is a colored center that comprises of a substitutional nitrogen and a lattice vacancy. Why is it important? It is closely related to a useful property, which is photoluminescence. Photoluminescence is a consequent emission of light due to the absorption of electromagnetic radiation, which can be manipulated through magnetic and electric field. Let's continue on. So why is this a useful property? Before going into the details, we'll briefly go through the concept of quantum numbers. There are in total 4 quantum numbers that are necessary to describe the movement of each electron fully within an atom. According to the Pauli exclusion principle, no 2 electrons have the identical combination of the 4 quantum numbers. The first is principal quantum number n, which is the principal electron shell. It describes the most probable distance of the electron from the nucleus. Second is the orbital angular momentum quantum number L, which determines the angular distribution. Then comes the magnetic quantum number ML, which establishes the number of orbitals and their orientations for the subshells. Last is the electron spin quantum number ms, and we would like to focus on this. It is independent of the other 3 quantum numbers. It classifies the electron spin direction by either having plus half value, which indicates the electron spin up, whereas minus half value is spin down. This quantum number is crucial because it is related to the generation of magnetic field. For NV center in diamond, electron spin quantum number is very important. The electronic state of nitrogen vacancy can be first examined. The electronic structure of the nitrogen vacancy center, NV0, which is the neutral state, incorporates 5 electrons. 2 are from the nitrogen atom, whereas 3 come from the bonds with the carbon atoms that surround the vacancy. When external voltage is applied to the p-n junction made from the doped diamond in order to change its Fermi level position, it becomes a NV- negatively charged state. 1 electron is captured from the lattice, typically from the nitrogen donors, so in total it has 6 valence electrons. The NV0 state is paramagnetic. For most of the times, experiments are carried out on the negatively charged state, as NV0 is not magneto-optically active. Nitrogen vacancy center in diamond has 3 main electronic levels: the ground state, excited state, and metastable singlet state. Singlet state is when electron spins are paired in molecular electronic state, and the energy levels do not split when exposed to a magnetic field. The grounded and excited states are triplets, which means that they are further split into 3 spin sublevels. The electronic spin quantum number here is plus 1, minus 1, and 0. This is possible because electrons exist in pairs, so if they have the same direction of spin, plus 1 and minus values are possible. Due to the axial symmetry of the nitrogen vacancy center, the ms plus 1 and minus 1 states are degenerate, and the ms0 state is lower in energy. Here, degeneracy of an energy level means that there are 2 or more equivalent but different measurable energy states. The transition from the ground state to the first excited state, whose energy difference is called the zero phonon line, has resonant wavelength of 638 nanometers, and is excited at most wavelengths below 640 nanometers. The transition between the ms0 and ms plus 1 and minus 1 sublevels takes only a few milliseconds at room temperature. When the laser is beamed and electrons de-excite to the lower state, single photons are emitted. This is why NV center is important. It is a stable source of single photon emission at room temperature. The frequency difference between the spin sublevels is 2.87 GHz for the ground state and 1.42 GHz for the excited state. This is called zero splitting, which is when the energy of 3 sublevels of the triplet seem to have separated, even in the absence of the magnetic field. To see its relation with the singlet state, the transition between the triplet, ground, and excited state occurs, spin is conserved. However, when the decay takes place via the intermediate singlet states, spin polarization happens, which is when spin is switched from plus 1 and minus 1 value to 0. Therefore, for the emission via the singlet state, fluorescence band is weaker due to the non-radiative decay between the singlets. Furthermore, when external magnetic field is applied, the energy level diagram changes. The Zeeman effect occurs, which is when degeneracy is lifted due to the magnetic field. It means that the electrons interact to give rise to two or more energy states. The two oppositely shifted sublevels of ms plus and minus 1 have frequency difference of 2 gamma Bz, where gamma is the electron gyromagnetic ratio and Bz is the magnetic field parallel to the NV axis. Here again arises the spin-dependent fluorescence property of the NV center. If we know the change in the fluorescence intensity, we can calculate the magnetic field applied. The most basic experiment to measure this is to record the electron paramagnetic resonance spectrum by slowly sweeping a microwave field over the electron paramagnetic resonance. Such optically detected magnetic resonance effect makes it possible to utilize the NV center to measure the magnetic fields with high sensitivity and nanoscale spatial resolution. This forms the basis of magnetic sensing applications. To summarize, the NV center has several key advantages. First is that it is bright, which can be detected individually with conventional microscopy. Second, the time required for such manipulation is extremely short. It is in tens of nanoseconds for the qubit manipulation. Moreover, it is operable at room temperature, which is a huge merit as temperature control is not required. Having these advantages, not only for magnetic sensing, but NV centers as a single photon source, has many applications, such as embedment in nanocrystals, scanning probe heads, quantum meteorology, and even ultra-secure communications. It can be used as the basic building block of a quantum processor, the quantum bit or qubit, that is operable at room temperature. Hope this video helped you with the understanding of nitrogen vacancy, center, and diamond. Thank you for listening.